Greetings, physicists. This video will be about solving conservation of energy problems. So let's get into it. We've got a little bug, desert locusts, which apparently can jump really high. And we've given the mass of this locust and how fast it can leap off of the ground at. And the two questions we're asking, which are sort of like the same question, is how high will he jump? And in one case we ignore the drag force of the air, and in the other case we don't ignore it. So here's my little locust. Hey, let's not do that. So he's got a body, head, thorax, abdomen, right? Do they have legs coming out of their head? Probably not. Okay, and he jumps. And he jumps up at 3.1 meter per second. And he has a mass of 2 grams, oh boy, which is actually 0.002 kilograms. And that's all they give us. So when you're doing a conservation of energy problem, you want to identify the types of energy you're starting with, and you want to identify the types of energy you're ending with, and the changes that are going to go on. So here's what's going to happen to this locust. If I draw it from the side, the locust is on the ground and it's going to jump up to some height, h. And it leaves the ground with some velocity, and when it gets to the top of its jump, it will have 0 velocity. So what's really happening to this locust is it's going to take some, we'll do a delta as a final minus initial, so its kinetic energy is going to do this. It's going to have a final kinetic energy of half mv final squared. Subtract its initial, that's the change in its kinetic energy, so half mv naught squared is what it starts with. Okay, that's the change in its kinetic energy. That should be equal to, well, what's its kinetic energy turning into as it goes up? It's turning into height. So whatever kinetic energy it loses should be the height that it gains. So I'm going to say that the negative of the change in kinetic energy will be equal to the positive of the change in gravitational potential energy, which is the energy associated with how high off the ground you get. So we'll say that the change in height energy would be mg height final minus mg height initial. Now there are some things that are going to make this easy. We know that the v naught is, or the v final is 0, so this is 0. And we know that the height naught, it starts on the ground, is 0. So this simplifies pretty easily, and look how this negative multiplied by this negative will cancel. So I'll get half mv naught. Can I write 0? That would be awesome. Half mv naught squared will be equal to mgh. So we're just changing the energy from one type to another. We're changing kinetic to gravitational potential. And we're looking for how high it's going to go. So I'm going to divide, oh look, the mass of the locust doesn't matter. That's fun. So I'm just going to divide by g, and I will get v naught squared over 2g will be my height. So what I'm plugging in, I know the v naught was 3.1 meters per second. Square that, divided by 2 times 9.8 meter per second squared. All right, calculator, lay it on me. 3.1 times 3.1 divided by 19.6. And I'm getting 0.49, let's see, seconds squared will cancel, 1 of the meters will cancel, and I will be left with meters. That's the height. And this is a 2 sig fig answer. That's how high he jumps. Almost half a meter for a locust. For 2 gram locust, hey, that's a lot. And then let's go up here. Oh boy, I did one of these again. If 20% of its kinetic energy is lost to drag. Okay, so we lose some kinetic energy. What a drag, man. All right. Well, if 20% is lost, then you're going to have, let's do this. I'm going to do it like this. The kinetic energy that it started with, we had said was equal to the gravitational potential energy that it ended with. Well, what we're going to say is that we're losing that, so that's kinetic energy, and we're losing 20%, so minus 0.20 of that kinetic energy is now going to be equal to the GPE. And so if we subtract that out, what is that going to be? Well, that means that 0.8 is left, so 0.8. So 80% of the kinetic energy is still there, and that's what gets turned into gravitational potential energy. Now let's look at gravitational potential energy. Gravitational potential energy, so if I have 80% of that kinetic energy, I will also end up with 80% of my gravitational potential energy, and gravitational potential energy and height are linearly related. It's a 1-to-1. So I will just get 0.8 times the height, 0.80 times 0.49. So I can do that on my calculator right now. And so what I'm going to get then, 80% of 0.49 looks like 0.39222, but I'm rounding to this because, again, it's a 2 sig fig problem. So I'm going to get this many meters. So almost 2/5 of a meter. Okay. That's how we're going to do that one. Let's go on to the next one. Ooh, water slides. I looked this one up. The Summit Plummet is almost a vertical water slide. It is so steep, and it's really tall. Again, they mark it here. It's 36 meters. Now, if you can't visualize 36 meters, remember our classroom is about 3 meters tall. You might be able to say 5 meters tall if you include the insulation above it. So maybe a 1 meter building, or a 5 meter building is like 1 story. So this is maybe 7 stories tall. If you've ever watched Olympic high diving, the Olympic high dive, the really tall one, the platform, is only 10 meters tall, right? So this is an Olympic high dive, maybe a third, less than a third actually. It's actually closer to a fourth of this particular water slide. Look at it, Google it. Oh my God, it's so huge. Anyway, just trying to scare you. So we put a rider up there, and they're going to go and slide down it, and then hit the bottom. And the question here is, how fast will they be going? And again, we've got a couple of two scenarios. We have the scenario where they start moving at 2 meters per second, and we have the scenario where they they just go from a dead start. And we want to see how fast they will be moving at the bottom. We're ignoring friction. It's a water slide. We assume it's pretty slippery, and also it's very vertical. Whew. How to start this one? Well, notice they don't give us mass, but if it's like the last problem, that won't matter, right? So they're starting with MGH. Starting with MGH, this person has some MGH initial. Subtract. Oh, hold on, that's MGH initial. I gotta go back the other way. So the MGH final minus the MGH initial will be the change in gravitational potential energy. Equal to, on the other side, it should be whatever the change in gravitational potential energy, it's turning into kinetic. So we would say the half mv final squared minus the half mv initial squared. But again, it's how much height energy we lose, how much potential energy we lose that turns into kinetic energy gained. And some things will help, right? When you're at the bottom of the slide, the final height is 0. So that part goes away. When they're starting, Well, the first question was, what if you started at 2 meters per second? So we can't actually ignore the starting speed. And notice the negative will multiply through, and we will get a positive here. So we'll get MGH naught equal to half mv squared minus half m v naught squared. And what we're trying to find is the final speed when they get to the bottom. So let's look at that. Scrolling here. To isolate that, I'm going to add this term to both sides. So I will get mgh naught plus half mv naught squared equal to half mv squared. This is another way to write the law of conservation of energy. The original one that I had written is all the energy all of one type of energy that you lose equals all the type of energy that you gain. But what this is saying is all the energy I start with, all the h naughts and v naughts, equals all the energy that I end with. And I could add plus MGH final, but we knew that MGH final was 0. So this is another way to say the law of conservation of energy. Mass doesn't matter. Good, we weren't given mass, so that will cancel. And then I want V, so I'm going to have to multiply by 2, it looks like, and square root. So I'm going to get 2G H naught plus V naught squared square root equals V. Good. Well, what do we have there? 2 times 9.8 meter per second squared times the height we start at is 36 meters plus V naught was 2 meters per second, and if we square that, that's going to be 4 meters squared per seconds squared, and I have to square root that. All right, let's plug that in. I'm going to have the square root of 2 times 9.8 times 36 plus 4. And I got, oh boy, that's scary. 26.6, which in a 2 sig fig problem, this is actually 4.0 because it was 2.0 originally. So yeah, there's definitely a 2 sig fig problem, so we'll round that to 27. And if you notice, I have meters squared per second squared. This is a meters times a meters, which is squared. And when I square root all of that, I will get meters per second. 27 meters per second. Remember, 29 meters per second, that's freeway speed. That's 65 miles an hour. So when you take this water slide, again, assuming that there's no friction, you're hitting the end at freeway speed. It's like you are a car. That's why this. I would definitely not go on this water slide. This sounds like a recipe for injury if anything goes wrong, or at least road rash or something, or a huge wedgie. So that was if we started at 2 meters per second. Then let's look what happens if we don't start at 2 meters per second. What if we start at 0 and hope that we end at a reasonable speed? Well, let's see here. So if we start at 0, so then we have mgh naught. That's all the energy we start with. We're not going to start with any kinetic energy. And that has to be equal to all the energy we end with, which is half mv squared. Because we don't end with any height energy, and we don't start with any speed energy. So those are the only two terms. The mass will cancel. And the v will be equal to the square root of 2gh naught, which is the square root of 2, 9.8, and 36. Okay, so let's put that in. Square root 2 times 9.8 times 36. Well, what do you know? 26.5, which in a 2 sig fig problem is really 27 meters per second. So look at the difference actually between the unrounded answers, 26.5 and 26.6. your starting velocity makes almost no difference to how fast you end up. Literally like 1%. There you go, ladies and gentlemen. So next time you go to the water park and you're starting at the top of that slide, whatever slide, hopefully not this one. It doesn't matter which one you start at. It doesn't matter whether you give yourself a push or not. You will get the same thrill no matter what. Man, that's painful. Okay. Spring. Here's some elastic energy, okay? Spring-loaded gun is going to launch a plastic ball, so I know there's going to be some stored elastic potential energy, and the question is, what is the ball's speed as it leaves the barrel? Okay, we can do that. So if we're drawing this, so you have the gun, like so, with a big spring inside, and you're going to put the ball in the barrel, and when it goes all the way back, so I've kind of drawn this backwards, right? So you put the ball in, it's going to click back here where the trigger is, and then, so if this is the bottom picture is the starting picture, then the top picture is after I've pulled the trigger and the spring launches the ball out the barrel. So it's leaving with some velocity. So the interval that we actually care about is really from where the ball starts, which is back here, to where the ball ends, which is right there. That's the interval. It's the interval where the ball travels the length of the barrel. We're not actually going to, this problem doesn't ask us anything about what happens after that. And so we know the length of the barrel is 10 centimeters, at least as far as we push the ball in. We know the spring constant. We know, so length, spring constant, mass of the ball. We know it's all horizontal, so we don't have to deal with gravity in this one. So let's figure out what our equation is going to look like. Well, the type of energy that on one side is the elastic potential energy. So there's going to be a half kx squared minus a half kx naught squared. That is the change in elastic potential energy. That change in elastic potential energy, it's being turned into kinetic. So we have a half mv squared minus a half mv naught squared. But again, it's how much of this we lose versus the other side, how much we gain. So I make the left side negative. So if this is the starting condition here, we're starting with a big compression of the spring initially, and when we end up here, we don't have any compression of spring. It's back to equilibrium, assuming that the spring here is unstretched. It's pushed back to where it was not stretched. So I'm going to say that this x is 0, the final stretch of the spring, and the negative will multiply through, and I will get a 1/2 kx naught squared on this side. I'm also going to make an assumption here that when the ball is held onto the spring before we pull the trigger, its initial velocity is 0, so that makes this term 0. So the half kx squared will be equal to the half kx naught squared will be equal to half mv final squared. Oh, look, the half goes away. That's nice. All right, so now I just need to plug in things, and I'm looking for v final. So in this case, the mass matters. We can't cancel the mass. So K was 10 newtons. Oh, hold on, before I do that, I'm about to solve it backwards. Let's go ahead and let's just solve it algebraically first. And so I'm going to divide by the m on this side and get K x naught squared over m equal, and I have to square root that. Should equal v. I could even pull the x naught out of the square root, so I could get x naught square root k over m equals v, which I guess would make the calculator easy. Probably not. So the x naught was pushed back, I think, 10 centimeters. I need to look that up, though. 10 centimeters. It's all 10. 10 newtons per meter, 10 grams, 10 centimeters. Okay. I'm going to change everything, though, into meters and kilograms, just because I'm OCD like that. So the x naught was 10 centimeters, so I'm going to make that 0.1 meters. really 0.10 because that's how many sig figs I have. 0.10 meters times the square root of K, which was 10 newtons per meter, over the mass. It was 10 grams, but if I'm in newtons, that won't cancel, so I need it to be in kilograms. So it's going to be 0.010 kilos, and that should be equal to my V. All right. Well, I would not put what's under the square root into your calculator because we're just dividing by 10 to the minus 2. So that's an extra 100 on top. So what this really is 0.1 meters times the square root of 1,000. And when, now this is tricky with the units. I'll go ahead and show you down here. A newton is a kilogram times a meter per second squared. And then there's a meter there, so times a meter, or there's a meter squared on top. And we have a kilogram on bottom. The kilograms cancel. And then I have meter squared over second squared. So when I square root this, I will get meters per second. That's bothering me. I'm wrong, because this is a newton per meter, so that meter is on the bottom. So instead of that meter being there, that meter is actually down here, where it will cancel with the 1 on the top, and I will get 1 over seconds squared. When I square root it, I will get 1 over seconds under the square root. That makes more sense because I have a meter out here. Okay, let's do this in the calculator. 0.1 times the square root of 1,000 equals 3.16. 3.16 meters per second is how fast that toy gun launches that ball, which is, it's a toy gun. That's probably about right. Oh, and this is a 2 sig fig problem, so this is going to get rounded to 3.2 meters per second. 2 sig figs. Tens, all tens. Okay, that's that one. So we've had one kinetic to gravity, we've had one gravity to kinetic, and we've had one elastic to kinetic. Let's go to the next one. We have Quinn on a slide, and it's tipped to 30 degrees, got it, moves down, and they tell us his speed at the bottom, and then they ask how much thermal energy is deposited. So apparently there's friction on this slide, and we haven't done a lot of work with friction, but it happens. And whenever there's friction, whenever friction does work on something, you always lose that energy. Friction is what we call a non-conservative force. Energy or work done by friction just gets lost as heat, which is going to make the slide hot, and it's going to make the trousers hot. So let's draw this. We've got Quinn. Here's the slide. The slide is 5 meters long. Okay, they don't give us the height of the slide. 5.0 meters long. They tell us it's at an angle of 30 degrees with the horizontal. Moves, and when he gets to the bottom, he'll be moving at 2 meters per second. Well, let's do it this way. All I need is the height first, because the angle shouldn't make a difference, right? It's only how far he falls. The length of the slide will make a difference if there's friction, if we were calculating it that way. But so I'm going to redraw this slide like a triangle, and it's the vertical leg of that triangle that I care about. So it's a 30-degree angle, and I have a 5 hypotenuse, and I need the opposite here. So this is a sine. So this should be 5 sine 30. Is the sine of 30 a half? I never remember. 5 sine 30. Nope, that's not what I wanted. 5 sine 30. Bad calculator. There you go. Yep, it is a half. Okay. So 2.5. So the vertical leg there is 2.5. Where am I going to write this here? So the height is 2.5 meters. So he drops 2.5 meters, and that I can use in an energy problem. So what I'm going to do now, just so you know, I'm going to calculate how much energy, if there was no friction, how fast should he be going at the bottom. And that will tell me how much energy he's actually lost. So go down here. 2.5 meter height. So we have an MGH final minus an MGH naught. And whatever height we lose turns into whatever speed he gains, which is half mv final squared minus half mv naught squared. And I know a couple zeros. At the top of the slide, I'm assuming he does not have any velocity, so his initial velocity should be 0. And at the bottom of the slide, he has no height, so his height final should be 0. The negative will multiply through, and I will get his MGH naught equal to half mv final squared. Again, this is without friction. So without friction, mass cancels, and I am looking for final velocity. So final velocity will be square root of 2gh naught. And we just figured the h naught, that's the square root of 2 times the 9.8 meters over second squared times the 2.5 meters. So let's do that in the calculator. Square root 2 times 9.8 times 2.5. 7, a perfect number. Or a perfect, never mind, not perfect. Anyway, 7.0, because I'm doing 2 sig figs, meters per second. That's how fast he should be going. Why does that sound too big? I'll believe it for now, maybe. Okay. He ought to be going 7 meters per second at the bottom of that slide, but he's not. He's actually going 2. So he's lost some energy. So he's lost 5 meters per second worth of energy. So let's figure this out. Okay, can I scroll? That would be really awesome here. So he has 7 when he should have 2. So this is how much kinetic energy he has. He has 1/2. Well, do we know his mass? It's like 24 kilos. Yeah, 24 kilos. Okay. So we have half of 24 kilograms times what his real speed is. His real speed is 2.0 meters per second squared. But that's what's left from what should be 7. So he should have this, half 24 kilograms times 7 meters per second squared. And if I subtract those values, the difference between what he has and what he should have should be how much he's lost to friction. So, real quick, 7 times 7 times 24 divided by 2. So this is his potential, this is his maximum energy, this is how much he should have, minus, what do we got here? Half and 24 into squared. He only has 48. Ouch. So he lost a lot of energy to friction. And you can just subtract the 8, 58, 580 minus 40 is 540. So he lost 540 joules. And that's how much went into the slide, went into his pants, the rubbing surfaces essentially. So he lost almost, what, probably 90% of his energy to this slide. Good grief. That's probably true of most things. I mean, 7 meters per second is no slouch. That's pretty fast. So if all the kids came zipping down the slide at 7 meters per second, more kids would probably get hurt on the playground. So maybe having friction isn't such a bad thing in this particular case, assuming he avoids like burns and stuff from it. That's why you wear pants on the slide, ladies and gentlemen. Do I have more? I do have one more. Okay. At the water park, Katie, all these slides, is going to slide down each of the frictionless slides. So she's at the water park, she's trying all the slides, she always starts at the same speed, and we got to rank them. Where is she moving the fastest? And this is basically a trick question. The hardest part of this question is that I drew the slides poorly. But if they were actually at the same height, which it looks like they are, right? This is pretty much the same starting height, same ending height. Then it doesn't matter because there's no friction. If there's no friction, then it doesn't matter how long the slide is itself. These slides are longer, which means it will take her more time to get to the bottom, but she will be falling through the same height, the same MGH. And if the MGH, nope, don't want that. If the MGH is the same, then the half mv squared at the bottom be the same. And if the mv squared at the bottom is the same and her mass is the same, then her velocity is the same. So she will go the exact same speed no matter which of these slides she takes. It'll just take her longer to get to the bottom. Now, if there were friction, just in case you encounter this on a test, if it does not say ignore friction on this slide, then the slide that has the longest distance will be the slide that produces the most friction or does the most work with friction. Because essentially, every meter that you rub against the slide is doing work, right? Work equals the force that you feel times the delta x over which you feel it. So the longest slide will have the most friction associated, which means you will be going the slowest at the end of that slide. So A would be your best choice if friction was involved. But since it's not, they are all equivalent. Okay, hopefully this helps you in solving conservation of energy problems.